All right, so let's start, guys. Welcome all to lab session number 4 of this deep learning course. And let's continue our discussion into deep learning. And so now I think we're slowly getting into the real deep learning. Till now, we've seen the basics, fundamental blocks of deep learning. Now we're actually getting to deep learning. So, very exciting lab today. First thing first, I'm going to share the lab notebook. And I request you all to open a Google Colab notebook where we can start, like writing code. So, but this is the link to the notebook. And all right, we'll sort of go through the basics of what. Okay, so this lab session we're actually going to be covering computer vision and right. And so what exactly is computer vision? Computer vision is basically AI that deals with how machines can sort of perceive visual data, including images, videos, just like we do. And I think I don't need to tell you guys the importance of this because even in humans, vision is probably the most important perceptual component. And our senses, and probably the most developed as well. So it it's I think it's only natural that this domain of AI, which is computer vision, is sort of the most advanced as of now, in comparison to all other sort of domains. And so just to give you an idea, the most important conference in AI is called CVPR. It stands for Computer Vision and Pattern Recognition, and that's completely based on computer vision. And each year it has around 25,000 submissions or so. So quite a lot, quite a lot. And so there is one particular class of models which is particularly interesting in computer vision, which is known as convolutional neural networks. So we're going to look at that. But first things first, let's actually set up our data, just like we did last time. So we'll actually go through it again. One more thing, guys. On the website of this course, which is ketawari.in/dl. And if you go to the lab sessions, we'll actually see that lab session number 4 was dedicated to image segmentation, but I think that we're going one lab behind in schedule. So that's okay, we'll update it. So lab session number 4 is on computer vision. All right, so we are going to be using PyTorch. So import torch. There is a sub-library in PyTorch, which is known as Torch Vision. And it has everything related to computer vision in it. All right, so we're going to need to import that as well. All right. If you guys remember that we imported things like nn.module. So that's actually very important. So otherwise you'll always have to write torch.nn. Things like that. So it's directly, it's quite good to directly import nn. So I'm just going to do from torch import nn. And if you guys also remember, there was another submodule within NN which was functional, which contained a lot of functions like metrics and loss function and whatnot. So that will actually come quite handy. So torch.nn, sorry, from torch. Oh, sorry, import torch.nn.functional as. I'll just name it capital F because it's quite the convention to do so. All right. All right. Let's see if this works. Yep. Also, guys, if you guys have any doubt at any point, feel free to stop me, and I'll probably go through the concept again. All right. We are going to be actually dealing with this data set called MNIST data set, which we talked about, which was which we've been working with for quite some time now, which is handwritten digits. So, but now we're going to be downloading it directly from Torch Vision. So, just to show you, Torch Vision actually includes a lot of standard computer vision datasets as well. So, for example, if you come over here and you find Torch Vision.datasets, and you'll find MNIST over here. Yep, here it is. Yep, here it is. So, the way you would import that would be, so I would need to, if you see that you need to download the training data set and the testing data set separately. So in this function, you would put true if you want to download the training data set, and a validation data set or training data set, one and the same things. You would put them, you would put a false in that place. So you would go torchvision.datasets, right? .mnist, all in capitals. Root is equal to, now I'm just following the API over here, right? So root, root, which means basically where do you want it to be downloaded? We'll say just download it over here. Download equals true, because you want to download it and not just want the like auxiliary sort of object which does nothing. You want to actually download it. Transform equals train is equal to true. Train is by default true, but anyways, let me just mention it. Transform, which means like what exactly do you want, what function do you want to be applied on all the images. Over here, what we're going to do is we're going to convert them into tensors, because that's what's going to be useful to us. So by default, this would probably give us like PIL images or like images in general. We don't want that, because that's of no use to us for most of the times, and we'll have to separately do that for everything. So why not just directly like apply tensors at the beginning? Was anyone saying anything? Does anyone have a doubt? All right. So similarly, we go for validation images, and you would go download is equal to true as well. But now train is equal to false, because you don't want the training data set, and transform remains the same. I'm just going to copy paste this because I'm lazy. Yep. And let me just see if I get the training images correctly. Oops, there's an error. Torchvision.transforms does not have an attribute to tensors. Oh, it's tensor, not tensors. So please be careful about that. Yep. So 60,000 images in our training data set. And if you again go to, let's say, your validation images would probably be 10,000, I think. Yep, 10,000. All right. And then next step, once you, so let me just put in a text over here. Downloading dataset. All right. Once you have a dataset, now dataset itself is of no use to us. We always convert it into another data structure, which is known as a data loader. And what data loader essentially does is that it basically puts images in batches, and it puts them into GPU or CPU or whatever you want to use them to. So this lab session, we're also going to be using GPUs. We're going to see how you actually train your models on GPUs using PyTorch. All right, so now the data set has to be converted to data loaders. So if you guys remember, now data loader is essentially a very simple class in Python, and I think we may have seen like the structure of it. But even if we haven't, it's actually nothing too difficult. But anyways, we're going to be using the class which is already provided to us from PyTorch. It's nothing complex. You can look at the source code. So torch.utils.data import data loader, all right? D capital, L capital. And now, so now train DL would be data loader, MNIST train images. Batch size would be, I think 16 is a good size, like batch size. And now valid DL, which is going to be data loader, MNIST valid images. The batch size can now be double the size, only because validation data set does not usually deal with gradients, and so you're essentially saving half of the space. Like when you say batch size of 16, you're actually going to be saving parameters with respect to those, as well as the gradient values as well. But you're not going to have to do that for validation images, so you can essentially double the size of validation data set. And mind you, like, it's always good to have as large as a batch size as possible, because then you're getting rid of sort of variations as such, because you will then be averaging over a larger subset of the data set. And so statistically, it's going to be much more stable than, let's say, a very smaller data set, because you're going to be getting rid of a lot of statistical biases. But the only constraint you then have is how much can your GPU actually handle at once. So now that we are getting a chance to increase the size of our batch, it's always better to do so. All right, that is done. We're going to be now creating our model. All right. So if you guys remember, and so now we're going to be actually dealing with what is known as a convolutional neural network. So we actually did go through what exactly a convolutional neural network looks like, but let me just show you again. All right. So okay, let me actually leave you a link to this notebook as well. So this is actually a blog post that I wrote probably last time. Last year, actually. So, but let me actually show you. It's actually quite illustrative. Right. So if you guys remember that this was your standard neural network that we saw last time, which was sort of this. There were inputs, and we had certain linear layers, and then you pass them through that, you pass it through some function, and then you get some another state, which is over here, this thing, and then you pass it through another linear layer, and finally you get some output, right? Now, when we actually passed our MNIST data set into that, we first like flattened it. So in the sense we converted a 28 by 28 by 1 image into one single long vector or a tensor of 762 pixels or 64 pixels or whatever that was. And so the only disadvantage with that is that neural networks, or the standard multi-layer perceptron neural network that we looked at, does not take care of spatial relations. You know what I mean by that is that, look at me, okay? Look at my face, for example. This image that you're seeing on your screen is probably a collection of pixels, right? And now the thing with images is that one single pixel actually does not give any meaning. So if I give you a 0 value, which is black hair over here, or whatever value, you probably cannot tell that this belongs to hair, right? But a collection of pixels is what gives you sort of relation. So a collection of pixels is what forms a hair or my face or my eyes. A collection of pixels is what forms a dog or a cat. A collection of pixels is what forms. So an individual pixel is not useful to the machine or even to us as possible, but a collection of pixels makes sense, right? So it's very important to like maintain that spatial relativity, in the sense that, you know, like there's a specific meaning to these particular pixels being together because they represent something. Like, you know, they represent the eyes or the nose or the face, and then collection of pixels becomes the entire face, and then the collection becomes the body, so on and so forth. Anyways, so how exactly do convolutional neural networks solve this issue? Here is how. So essentially, convolutional neural network picks up a small area at once and does not break them, and sort of processes them all at once. So that is how they work. And the way it works is that imagine that you have so the way it works is through an operation known as a convolution. All right, and this is what it looks like. So if this was an image, sort of this blue box over here, the convolutional neural network will sort of process this box of 3 by 3 at the beginning, at the first, all at once. All right, and then it would process it through this convolutional function, of course, and then it would sort of keep on sliding throughout the image to process the entire image at once. So you're sort of maintaining that spatial relations between that. All right, so what exactly is this convolutional operation? This convolutional operation is nothing but a multiplication operation, sort of. And so what exactly happens is that imagine that this 3 by 3 matrix at the very beginning is being processed. What you would exactly do to process that is that you would sort of multiply it with this matrix over here, and I've sort of predetermined this matrix. Now this matrix is called the convolutional kernel. All right, this is what carries out the multiplication. And so it's nothing but 1 1 1 0 0 0 minus 1 minus 1 minus 1. And all I would do is sort of multiply each element in place. So 7 times 1, 4 times 1, 3 times 1, 2 times 0, 5 times 0, 3 times 0, 3 times minus 1, 3 times minus 1, 2 times minus 1. All right, and it would give me a value, and this will all add up to be 6, let's say. And now let me slide this convolutional kernel 1 pixel to the right. All right, and so now my 3 by 3 matrix becomes 2 5 3 3 3 2 and 3 8 8 over here. All right, and so I would do a point by point multiplication. I would get minus 9, and I would sort of keep on sliding. Now once I reach to the rightmost part, I would go back to the originals window, and I would now, instead of going right, I would shift it down, and then I would keep on doing that operation. So I'm slowly going through the entire image. All right, now this is called a convolutional operation. What does it signify? Okay, let me tell you that as well. So this convolutional kernel is actually designed to do some very specific things. All right, so a particular convolutional kernel has the ability to identify certain features. This over here, for example, is very good at identifying straight lines, vertical lines. All right, so any vertical contrast, so vertical lines in the sense that anything that is black to the left and black to the right, but the line of separation is a vertical line. This convolutional kernel is very good at identifying that. And why is it important? It's important because and so there would be, let's say, another convolutional kernel that would be very good at identifying horizontal lines, or a diagonal line, or let's say circles, or like a curve like that, say, or let's say a sort of a shape like this, and so on and so forth. And so whenever it's actually going to come across an area of a pixel, that 3 by 3 area of a pixel, which actually has a straight line, this is going to give the multiplication output is going to be a very high value. So when you see 6 over here, it essentially means that this 3 by 3 kernel actually had a straight line. All right, but this 3 by 3 area did not have a straight line, which is why the activation value, or like the output of the convolutional kernel operation, is actually very low. And so the higher the value, which it means that the feature exists over there, and then so that becomes one convolutional layer, so that is what essentially replaces. So now what we're going to do essentially is that we're going to be so when we did linear operations over there, we're going to replace them with convolution operations. So we're going to do convolution operations, then we're going to apply an activation function, then we're again going to do a convolutional operation. And so after each convolutional operation, you're going to get certain features. and on top of those features, you're going to again apply some convolutional operations, and so you're going to be able to identify much more complex features. Let me just show you something very, very interesting. I don't know if I've mentioned it over here. Probably should have, but yep. Look at this image over here, and let me actually show you like how, like, as you keep on progressing further and further into the convolutional neural network, how complex features, how, like, what level of complexity can neural networks identify. So the very first layer, if you guys look at over here, this is actually from a paper from 2013 from Zeiler and Fergus, very good paper. You'll see that this neural network can only identify very basic shapes, like, two lines at once, or like say a green image, or like say a sort of mixture of orange and blue pixels over here. That's it. All right. But in layer 2, which is this thing, you can see that this neural network can identify much more complex things. Like it can now start to identify white circles with black center balls in them, or let's say this kind of a shape, which is um, sort of a blue ball with a green writer arc towards it, or let's say this over here, which is a lot of lines going parallelly. Let's go to the next layer, which is layer 3, and now you can see that the convolutional neural network can identify even more complex things, like, sorry, so this is layer number 2. So these two are the same thing, but like in different formats. And this is layer number 3, and now you can see that this model can now identify like web-like structures, like honeycombs and boxes and stuff like that. It can identify white backgrounds with something towards the top left. It can now identify flowers. It can now identify tires of cars. Look at this block over here. It can identify orange pumpkins. It can identify people. So it's finally identifying people as well. And it can identify flowers, like a particular type of flowers. It can identify barcodes. So, like, can you imagine how complex our networks? And so, if you can imagine, like nowadays, you have neural networks that have 150 layers, or let's say 200 layers. What level of complexity can you achieve using that? So, it's quite fascinating. So, that essentially is a convolutional neural network. Enough about this. Let's actually start coding it up. All right. So, what I'm going to do is that I'm going to be writing a function which is called def get CNN model, which stands for Convolutional Neural Network Model. And the way you design it is you do a lot of convolutional operations. And the thing with convolutional neural network operations is that sorry about that. That if you look over here, that this is a 5x5 image, like 5x5 pixels. When you apply convolution operations, you always end up with a smaller matrix. So now 5x5 turns into a 3x3 pixels, and then you would apply another convolutional operation on that, and becomes even smaller, and so on and so forth.
Hey, in this, shouldn't the minus 9 also mean that it is a straight line? Like you told in that.
Why do you think so?
Because if I invert this kernel,
Mhm.
so that would also mean that if
Not
I
necessarily.
minus
Invert meaning?
1 and like that, if I have, so
So
it would be,
are you saying that if this was -1 -1 -1 0 0 0 1 1 1, it would give me like +9?
yeah.
No, it won't.
Mm, okay. How?
It won't. It won't. It won't.
Okay.
Uh, though, okay, I'll tell you what it means. So you see 1 over here. So 1 multiplied by a positive value will give you a higher value, and -1 multiplied by a negative or sort of smaller value will end up in the entire result being a higher value. That's it. And so in computer vision, white pixels are usually high values and black pixels are low values. And so this kernel would then essentially be good at identifying white to black transitions as such. All right.
Okay. Hmm.
Now, in any other configuration, like let's say if black was over here or white was over here, now it may or may not be possible that, I mean, yeah, you're going to get a lower value, but it does not necessarily mean you're going to get a negative value.
Okay.
Yeah, yeah. And so it does not really matter if you think it in that way. I mean, essentially, what you're looking over here is that this convolution kernel is good at identifying white to black
Yeah.
transitions. And so what we're essentially going to do is that we're going to be running at every layer, we're going to be running, let's say, 16 or 32 such convolutional operations in parallel. And so one of them is going to be very good at identifying white to black transitions with vertical lines in between. One of them is going to be good at identifying horizontal lines. One of them is going to be good at identifying green color. One of them is going to be good at identifying red color, and so on and so forth. And so, yeah, we're going to be using that. We're going to be using that essentially. All right. Yeah. Any other question?
No.
All right. So I'm going to be creating a CNN model, and the CNN model essentially at the end is going to have a lot of convolutional operations going on, but finally you're going to have a sort of you're going to have a 2D matrix left in the end anyways. So now how do you deal with that? Because ultimately the output that we see has to be like sort of two linear layers. So we're going to have to then flatten them just the way we did our MNIST pixels in the beginning. So we're going to convert that 2 into 2 into a long vector. And then we're going to get a result. So anyways,
Aren't we going to use classes for this? Why are we going back to functions?
okay, sure.
I mean, I don't prefer classes, but which the better option?
So I'm going to be returning a class anyway. So this is a helper function. This is
Oh,
this is
okay,
not
okay.
a this is not I'm not constructing my class over here. Though I'd like to correct you, classes are actually the proper way to go about things. But the result of this is going to be a class itself. This is a helper function. I'm not constructing everything from scratch at such. You'll find out. Give me a second. So the first thing I'm going to be I need to first check if this input that has been given. This is just bookkeeping, not necessary. So this is an integer, because if someone passes a 10.5, it's going to be an issue for us. So assert type num classes is equal to int is equal to int, right? Now I'm going to be using this. Okay, so what do I essentially need to pass in? Okay, so let me just type in layers is equal to what do I need? Okay. First thing first, I need to pass it through a convolutional neural network. So nn.conv2d, all right. And let's actually look at what conv2d looks like. PyTorch. All right. So conv2d, is actually this convolutional kernel that operates on 2D images, and so it expects everything to be of the input size n comma channels, number of channels. So over here the number of channels is 1, and height comma width. So that's going to be input to this convolutional kernel. All right. And so height and width over here would be 28 and 28 respectively. Cn would be 1, but then we're going to go on to color images, and then Cn would become 3, and then n would be batch size, like the 16 over here or so. And I think it's always a good thing to insert sort of a resizing operation, which always makes sure that the input is of this condition, of this sort of shape input, because if it's not, it's going to throw us an error. So for that, I'm going to create a sort of a generic. So, okay, by the way, these all operations are classes in themselves. So every operation has to be a sort of a class. Now, I'm going to create a generic class which is going to take a function, because the only purpose of classes over here is to not only like create like sort of give us objects, but it also acts as functions later on, right? So nm.conv2d, we're going to use classes as functions, and we looked at how we do that. So for that, I'm going to actually create a generic class. I'm going to call it Lambda. All right, and again, it's going to be a child class of nn.module. And the way I'm going to initialize this is it's gonna take a function as the input. All right, always initialize nn.module, and I'm going to store the function. And the only purpose of this function is to like run the operation whenever you want it to, but in the form of a class. All right. So you're going to define def forward self x, and you're going to do return self.func x. That's it. All right. That's it. I'm also going to be defining this thing called as dunder repro, which is essentially what exactly gets printed when you run this class exactly. In the sense that if you remember that last time when I actually just typed model and it gave me a list of all the layers that were over there. So layer 0 convolution, sorry, layer 0 linear, layer 1 activation, layer 2 a convolution again, sorry, linear layer again, and then layer 3 was basically the output. So that was actually that was like, how does PyTorch know like what to print? It's only because what we actually tell it to print. And so that is actually done using this dunder repro. So I'm just going to do return f. F basically means string. I'm just going to type lambda. I'm going to type, so in curly brackets, which means that you can now put in variables into this string. So I'm going to type str self.func, which essentially means that whatever function you've done, just type it as it is in the terms of a string. And we'll look at what exactly looks like. So let me actually show you like what exactly lambda would look like. Now, what I'm going to do is that whatever functions I'm going to need inside these layers, I'm going to define them as functions first. But when I'm actually going to be feeding them as layers, I'm going to have to pass them as what you call as classes. So I'm going to be using this lambda function. So I'm going to actually need this later on. So I'm going to tell you what exactly is this used for. So x.shape, 0, which is, so I'm essentially what I'm doing over here is that I'm writing a function that converts a sort of a 2D matrix into a one long dimensional matrix, which we're going to be using towards the end of the convolutional neural network. So x.view basically changes the shape. So now essentially initially the shape was, let's say, 16, 1, 28, 28. Now you essentially want it to change it to, you want it to change to 16, 1 times 28, sorry, 1 times 28 times 28. So that's going to be the shape. Right? And so to do that, you're going to have to retain the first element, which is 16, all right, and the remaining basically get multiplied, all right. And so I'm just going to type a -1, which means that PyTorch is basically going to take whatever remaining elements and going to multiply them, or like put them into like if you want to fit like, so if it's 1, 28, 28, and you just have one dimension left, so PyTorch knows that you have to multiply them. So PyTorch is actually very good at handling them. I'm going to be writing a mnist resize function, which means that it's always good to sort of ensure that your input is of the same size as what PyTorch is expecting. So here I'm actually defining my function in a way that PyTorch will be expecting it to be 1, 28, 28. Now, even if you don't pass in that as batch and as a single image, PyTorch is gonna automatically convert it into a batch size of 1, because you're artificially adding another dimension, and that will act as the batch size dimension. All right. So it's always a good idea to probably put this before. So what I'm going to do is I'm going to pass in the lambda function over here and pass it mnist resize, because now I'm initializing an object. So it's a class, but it acts as the function which executes this function essentially.
Could you
That's
repeat what mnist resize does?
all right, sure. So if you go to conf2d over here, right, this documentation over here, PyTorch is expecting your input to be of this what do you call format, right? So the very last dimension is going to be the width, second last dimension is going to be height, all right, which is going to be 28,28. This is going to be the number of channels, so that's going to be 1 over here because it's a simple black and white image. It has only one channel, but color images then have 3 channels, so we're going to be changing that later on. And then there's n, which is the batch size itself. So if you guys went over here and did say what is next iter DL, and you printed x dot shape, it's actually of this shape, 16, 1, 28, 28, right?
Yeah, so then why do we need to?
Okay. Let's here I'm actually trying to create flexibility. So in the sense that if later on when testing, if anyone does not actually pass in a batch and simply wants to test it using one single image, they can pass it, and PyTorch will take care of it. It will not throw us an error at any point. So that's a very important part of software engineering in general.
Okay.
All right.
Thank you.
And later on, when we're actually going to be dealing with, let's say, more complex images, we're going to be modifying this function itself. So like when we're going to be dealing with, let's say, color images, so you're going to actually have to modify it. So you don't want to actually change the source code. Now the thing with convolutional neural networks is that the entire network is actually very dependent on the input size, and so you actually have to take very much care about the input size, and you'll find out why. But trust me on this one for once. All right. The convolutional 2D operation does not care about H or W, but it does care about what number of channels you're putting in and what number of channels you're giving out. And so let's say that you're passing it only one channel, and now our output channel is, let's say, going to be 8 over here. All right. So 1,8. So what essentially does it mean? There was one image of size, let's say 28 by 28. All right, there was just one channel. Now you have 8 different channels, and for each of those 8 different channels, there were 8 different convolutional kernels. So now you're actually defining 8 different features over here. All right. So this operation is actually taking 8 different times through 8 different convolution kernels over here. And so you have 8 different features. So one of them is going to identify horizontal lines, one of them is going to identify vertical lines, and so on. It asks for a kernel size, so basically the size of this matrix. So it's always a square, so usually it's always 3 by 3 by default. All right, but in the very initial layer you usually put it as a 5. I've usually seen people do that. All right, that's that. All right. Yeah, so initially it's going to be 5, but for all other layers, it's always going to be 3. It's a rule of thumb. It usually works well. So a 3 by 3 convolutional kernel always works well. All right. Next, there's something known as a stride and a padding. So what exactly is stride and padding now? All right. Now, let's look at this image over here, for example. All right. Or look at my image, for example. Now, I'm actually streaming at 720p, so which means that this image is 720 pixels by 720 pixels or something like that, right? So 720 pixels by 720 pixels is like what? Let's check out. It's about 5,18,400 pixels in total. When you apply a convolution kernel, the image size is going to reduce, but it's not going to reduce as much as you think. Like it's going to be so I mean, essentially what I'm going to get is 718 by 718. All right, so 718 by 718, sorry, 718. Now instead of 500 and whatever it was, now I have only 5,15,000. All right. And so that's the only reduction that one convolution kernel is going to have. And so in order to reduce it to, finally, we're going to have to come up to something which is going to be only, let's say, 1,000 pixels or something like that. Let's say something like that. You actually cannot deal with such large images. So it's actually, there's a lot of information that we don't need. So what people actually do is that when they're actually computing this convolution over here, when they compute the very first operation over here, they don't just slide it by 1 pixel, but they slide it by 2 pixels. So they're essentially skipping things in between. And so that difference, like how much bigger jump you want between each convolutional shift, is known as stride. In the initial layers, people actually set it as 2. 2 is very good because, and so what essentially is going to happen, you're essentially going to be reducing the size of the output by 2, because now you're skipping 2 times at once always. So now instead of 720 by 720, the image that I'm actually going on, I'm actually going to be left with 360 by 360. All right. And then the next step is going to give me 180 by 180. And so you're actually now reducing it at a good pace. And you will be surprised that we actually do not lose a lot of information over there. All right. And now there is something known as padding. All right. So what exactly is padding? All right. So padding essentially means to add certain pixels at the outer layer over here. So let me see if I have. Oh, let me show you images on Google Net. Why not? Slide and padding in CNN. Go to images. Let's go to GIFs. If I find some GIFs over here. GIF. All right. Yep. Notice how this is working over here. So this original image or this whatever feature we have is this blue box over here, all right? And this white layer that is added at the edges is called the padding. And I'll tell you why we add that. And now you see the stride is actually happen at a stride of 2. So it's actually skipping 2 pixels at once. Or is it? Yeah, it is. It is shifting by 2 pixels at once, if you look at it. Lengthwise as well as breadthwise. All right. All right. And so what exactly is the purpose of, let's say, padding then? Padding is actually needed because sometimes you essentially want the input and the output sizes to be similar or to be the same. Oh, sorry. I'll tell you why. Or what exactly is the purpose of padding? If you guys notice that a 5 by 5 image became a 3 by 3 image when you applied a convolutional kernel over that. And so that essentially, and then when you apply a 3 by 3 convolution over a 3 by 3 convolution, you're going to get a single value. So that's a 1 by 1 pixel, right? And now you essentially lose a lot of information now. Because even though initially you were actually doing a lot of strides does not lose information, but the image, the content within the image itself is now reduced to 1 by 1, and that is not enough to give you enough information about the pixels. So a padding, so what essentially you're going to do is that what you can do is that when the 5 by 5 image was converted to a 3 by 3 image, right, simply add a layer of 1 pixels on each edge, so now the image itself becomes 5 by 5 again. All right, and on that you can again apply a stride of 2. All right, and so you're going to be essentially, you're going to come up with and so you're not gonna lose a lot of information because of this padding feature, but also your computation is going to be much more efficient because of stride. So striding and padding are these two concepts that I use in convolutional neural networks. So I'm gonna, maybe you guys don't understand this, but I'm gonna put this in the homework part over here, which is read about padding and strides in CNNs. So just to recap, strides are used to save computation. So even if you skip 2 pixels at a time, people have seen that you don't, the result is almost similar. There's not a lot of difference. Padding is done to retain information within the image, right? But read about it. It's quite interesting. All right. So padding, I'm just gonna put a value like, I don't know, padding equals 2 as well. All right. So sure, why not? So that's my convolutional. So that's one layer, all right. So what's going to be my next layer? My next layer is going to be ReLU, of course. So everything's going to be passed through the ReLU function. Next is going to be another convolutional neural network. So now the input to that is going to have 8 channels because the output of this had 8 channels, right? 8. And now I'm going to say that the output is going to have 16 channels now, all right? So now on each of those 8 channels, I'm going to be applying 16 convolution kernels. I'm going to have a total of 8 times 16 different kernels that are applying over there. So you see like how we're increasing the complexity of features. 8 by 16. Kernel size will now be 3 onwards. Stride. Okay, let me just write it. Like
ReLU will act on each pixel separately.
yes, each output pixel, like not the input pixels.
Output of the coordinate, no?
Yes.
Okay.
Just like in linear layers. Right. 3. Stride again 2, padding equals 2. All right. So stride equals 2, padding equals. Do I want 2? Actually, I do not want 2 now. I'll tell you why. Because I've in the initial layer was actually worried about like how much original information I'm going to lose, but now so because I'm actually going to be using a larger larger kernel size, so I needed a larger padding as well. There is actually a formula to calculate like what exactly will be padding size, but you guys don't need to worry about that for now, because okay, even if I tell you, let's see, like what exactly is the purpose of padding? Padding purpose is to retain the size of the image itself. When you apply a 5 by 5 convolution kernel, you see that the image is going to be shortened by 2 pixels on each end. You can just visualize it if you want. All right. And so in order to retain that image back, you're going to have to add 2 pixels at the end. So that's the purpose of padding. And now when you're going to be using a kernel size, you're going to see that the image is going to be reduced by 1 pixel on each end. So essentially it's going to be reduced by 2 pixels totally. So 5 by 5 became 3 by 3 because it's reduced by 1 pixel on each end. And then, so in order to compensate for that, you're going to have to add one padding of 1. Right? That's that. And then ReLU again. I'm going to add another convolutional neural network, also convolution layer. So it's going to have 16 inputs and then 32 as the output. So again, kernel size will be 3, stride will be 2, padding will be 1, right? Followed by nn.ReLU, right? What else now? All right, let's add another convolutional kernel. This is conv2D. You can have 32 as the input, and I'm talking through practical experience. I'm not gonna do like a 64 over here, but I'm gonna do a 32 only. The reason for that is because the input pixels itself are of 28 by 28 pixels, so you really can't go too like how can you extract 64 features out of 28 pixels? Like a lot of information out of that is going to be very redundant, and so it does not make sense to actually have features which are larger than the input size itself. You always want to reduce them. So these are number of channels. Like, do you expect to get 32 times 32, or let's say 64 times 64 features out of 28 by 28 pixels? Does not make sense, right? I mean, you can do that, but a lot of that information is going to be redundant or maybe even non-informative, so it's not going to be of any help to us. So 32 by 32 is actually a good place to stop. Padding equals 1, followed by nn.relu. Right. All right. Now what I'm going to do, oops. These are my layers, by the way. And now what I'm going to do is that I'm going to use something known as an pooling. And what pooling essentially does is that it's going to average across all. Okay, so by the way, let's actually analyze what exactly will be the size of this. So there are 32 channels. So over here, the output was, let's say, let me actually do an enter over here, right? So the input was 16 times 1 times 28 times 28, right? Over here, it's going to be the, and the output was then 16 times 8 times something. So I over here, I know that for a fact that it's going to be 24 times 24. All right. Over here, the output is going to be, sorry, this is going to be 16, which is the batch size, times 16 times 22 times 22. All right, but you've applied padding, so it's going to remain the same. I mean, over here also padding is going to remain the same, by the way. So this way, and then 24 times 24, right? Over here, the output is going to be 16 times 32 times something cross something. All right, 16 cross, going to be 28. All right, this is going to be 16 times 32 again times something times something. All right. And now we need to actually bring it.
So this will be basically 32 times 32 in case of testing.
Sorry.
Like while testing, it will be 32 times 1 comma 28 comma 25. Like 28.
Yeah. Sure.
So basically, this is being handled by that resize function
Yes.
x dot u minus 1.
Yeah. Yes.
And so in flatten also, what is minus 1 at the end doing?
So
X.
-1 is basically going to be multiplying everything together, and it's gonna give us a sort of a single long tensor of 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 one dimension only, which is
Okay.
essentially sort of similar to a linear layer.
So it will multiply 16 into 1 into 20 into 20.
No, I'm
Okay,
retaining
16 will be
16.
separate. Okay.
I'm retaining 16.
Okay.
Now -1 basically is what I'm telling PyTorch, take care of the remaining. I don't want to care, but put it in this one dimension over here.
Okay,
All
got
right.
it.
So 16 is already taken care of. So PyTorch knows to multiply the remaining 3.
Thanks.
All right. So now I'm done with convolution network. So now what exactly happens with convolution? Because now the output, if you remember, has to be, the final output has to be 16 times 10, right? Because there are 10 classes. I'm gonna have to take care of these 3 over here. All right. So the very first thing that you're actually gonna do is you're gonna actually take care of individual filters. So what I'm going to do is I'm going to be using something known as an average pooling, which essentially pools, which basically takes an average across each of these filters separately. So there are 32 filters, and each filter is going to be, let's say, something, I'd say height times width, right? Height times width, right? So what I'm going to do is that I'm going to take an average across all of these 32 features. All right. So average of height and width. So I'm going to have 32 single values remaining. All right. So that's actually given in this very good function, which is nn dot adaptive average pool 2D. All right. Which means that you need to pool 2D layers across whatever number of channels exist. All right. And so I'm going to say that let's actually go to the documentation for this. It says that the input is going to be this, all right, and the output is going to be NC S0 S1, and S0 and S1 are actually determined by the output size which you put over here. By default, if you just put a single integer over here, it's gonna assume that S0 and S1 are the same. So you're basically saying that the output HN, you basically want to do an average across all the height times width pixels, and you want to put them into one pixel. So the output is going to be 1, right? Output is going to be 1. So essentially the size now is going to be 16 times 32 times 1 times 1. Right, which basically means that for each of these 32 pixels, there's going to be one value for each of these 32 channels. All right. So that is nn dot adaptive average pooling. Now, why not just average pooling? What is this adaptive over here? You actually have the option to convert this into any sort of shape you want, and PyTorch will take care of it internally. It knows what operations to take in order to get this sort of output size, and so what kind of averaging will be required. So as such, we don't want any complex averaging. We just want an average across all the pixels. So output is going to be 1. Finally, I'm gonna need to flatten this. So now my output needs to, and now I need to go to 16 by 10, right? So now I need to actually flatten this into this 32. I need to converge these 3 dimensions into one single dimension. I'm going to be using this flatten function. So for that, I'm going to be using this lambda function over here. All right. So lambda flatten. All right. And now from 16 times 32 to 16 by 10 is nothing but a linear operation. All right, does it make sense? So it's going to be simple nn dot linear. Input is going to be 32 channels. Output is going to be whatever number of channels you've included as the num classes. All right. And that, where is and that essentially is your layers, your number of layers within this convolutional neural network. Does it make sense? So now the output is going to be 16 by 10, which makes sense for us. So for each of these 16 images in the batches, you're going to have 10 predictions. One of them is going to have the highest value, which is going to correspond to our class. Does it make sense? The math also works out.
Yes.
All right. Thanks. All right. I'm going to be using this class. So now I can technically do, if I were to declare a class, I would probably do, I would do a def forward, right? And then I would pass everything through this layer and return it back to us. But I'm actually going to be using a much more convenient option to me, which is given by nn.sequential. What nn.sequential does is that it basically will take in all the classes that you have, and it will automatically define the forward function. It's going to define the initialization part. It's going to define um, uh, basically the GPU optimization part, or basically whatever, like if you remember, we had to declare everything as separate modules in the previous lab. So we don't actually have to do that now. And so I'm just writing a comment over here that nn dot sequential is basically a class given by PyTorch, exactly the same as the model we built before. And so what exactly did that model do? If you guys remember, we had to sort of initialize the super.init, so parent class, right? We had to declare each layer as a module, right? We had to do that. We had to define an explicit forward function, right? Stuff like that. We had to declare stuff like this, all right? We had to declare and then later on you actually have to take care of how GPU operations will work. All right. Now we've already done this. Since we've actually written this, I'm not actually going to be writing that from scratch now, because so our purpose over here is to optimize our code, right? And so why should you write something from scratch if you already have access to that? We did that once only for understanding purposes. Now we're not going to do that again. So sequential basically does everything. It basically takes in a list of all the functions that you're going to be using, all right, or basically all the functions, and it's gonna define them as like it's gonna operate on them sequentially. So when you give it an input, first it's gonna pass through this nn.conf, then it's gonna pass through the nn.relu in that order, right? And so that is the purpose of nn sequential. And so what I'm gonna do now is I'm gonna simply do return nn.sequential star layers. Star basically means that don't pass them as a layer, but basically pass all of the elements individually. Like, because sequential is actually just expecting you to pass them as arguments and not a list of arguments. So the star basically expands the list. Anyways, I'm gonna see if this works. I'm not sure. Let's see if this works. Let me just print this. Hopefully, there's an error. Unexpected indent. Okay, indent can be solved. Okay, so I'm going to say model is equal to get CNN model. So now you guys are going to see the model itself is a class now. So we're not actually reverting back to functions. This is sort of a helper function. All right. So helper function which returns the model class. In output is going to be 10. So let's see if the model works. Yep, so this is the model. You're going to see that there's a Lambda function. So this is a problem. I don't actually want this, like it to be printed like this. So I just want this to be printed. So what I'm going to do is that I'm thinking like, since this is actually a string, I'm going to separate this string and I'm going to using this first, I mean, this is the 0th word. And then this is going to be the first word. So I'm probably going to do that. So in the dunder repro. So now if you guys see, this conv2d was actually defined within PyTorch's nn.conv2d. So if you go to the dunder repro of this conv2d definition, you're going to see that this is actually printed. This is what the model asks. And now since there was nothing defined for Lambda, we had to define it separately using the dunder repro. And now I basically want it to be printed something like lambda mnest resize. So for that, I'm going to do lambda self.func. So after that str, I'm going to do a split. Now I'm going to take in the very first word. So let's see. Yep, better now. Yeah, this is much more readable as such. So that is how I'm going to be using this. All right. Okay, let's see if this model works. Let's see if that x comma y is still there. I'm gonna take this over here and I'm gonna paste it over here. But now I'm just gonna do model x dot shape and x dot shape as well. X dot shape. And now if you see this, I'm treating this class as a function only because we defined that forward function over there. Oops. Found the received an invalid combination of arguments, got none type, parameter, tuple, 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 int. Okay. What is the error? Oh, so I think there's some error in this mnest resize thing. Let me actually. So let's actually debug this. All right. I mean, why is it throwing us with an error? We need to probably debug this. Let's say mnest resize x dot shape untype. Oh, did I not? Oh, see, okay. Here's my mistake. I didn't return anything. Okay. Yep, works now. So I defined a function, but I did not return anything. So it's going to return none by default. So now it works, you see. So I gave it an input of 16, 1, 28, 28, and it's now giving me an output of 16, 10. Right. Now, I wanted guys to go to the last lab session or not, but we're actually going to be copying the loss functions and everything. Okay, so model construction is done. Now we define loss function. All right. I'm actually just copy pasting from last time. I'll probably paste it over here in the chat as well for those of you who do not want to go back. All right. But I recommend you do that. And so this is nothing but that basic cross entropy loss that we defined for a neural network. Essentially, look at this. The output is nothing but 16, 10. It was output was 16, 10 over there as well, and now it's 16, 10 over here as well. So the same things apply. We're actually going to see how we replace it with something that PyTorch defines by default. But for now, I'm going to keep this as is because I want to see. I want to actually show you that slow transition from the neural network to convolution neural network and see like how things are actually very connected. So like, for example, we first looked at how logistic regression neural network are the same. There is basically no difference at all except the linear layer construction as well as the loss function. So regression and classification is basically the only difference between logistic regression and linear regression is the loss function. The only difference between logistic regression and this neural multi-layer perceptron model that we did was nothing but the layer construction. And now because if over there I just had a binary classification, when I did a multi-layer classification, I had to extend that if-else condition that I wrote in that over there to a sort of a more multi-class approach. So this was that. All right. And now you're going to see that how multi-layer perceptrons and convolution neural networks are just basically very connected. And the only difference is again just model construction, and the rest of things remain the same because the output of the same is the same kind. I mean, even at the end over here, you see that there's a linear layer and there was a linear layer over there as well. So you see that how we have essentially solved the computer vision problem. Instead of breaking each pixel apart, we're now actually considering the spatial relations, and then we're actually going to be passing it through the standard linear layer approach that we used. That's that. This is that. Okay, we're done with that. Now we have to do, okay, so that is done. Now we need to create our optimizer. So if you guys remember, it was, I'd say it will be helpful if you guys simply just opened your notebooks. I can write it again, but it's basically the same class. So I'm just going to be copy pasting this. Or why don't you guys just open this link of this notebook over here and copy paste things. So I'm going to be pasting. Can someone please paste the link of this notebook on the chat for everyone to use? For anyone who came in late. Yep. So Priyansh has posted the link to this notebook over here. Guys, go over there and simply copy paste these few lines of code which you've already defined. And so you're going to see that a lot of these things basically are not even slightly different than what we did before. All right. Okay. Now, you guys remember why I mentioned at one point that I want to actually create this class over here to sort of give flexibility to the entire process? You're going to see now. All right. And so what I'm going to do over here is that I'm going to sort of redefine my MNIST. Or let me actually show you over there only. Let's go back and let's actually add some more functionality to this entire thing. What I need to do is that I need to, if you guys remember, we talked about normalization as well, and the purpose of normalization is always very helpful because it actually brings gradients to the same scale. And what you can do essentially is you can actually bring all of that functionality into one sort of one place altogether. So let me actually rename this as MNest pre-process. Okay, I think resize is not a good word. So I'm going to name this as pre-process. All right. And so over here as well, I'm going to have to change it. Pre-process. All right. I'm going to see if it works. And now what I'm going to do is I'm going to pass it through torch dot. Oh, just give me a second. Torch dot blah 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 torch dot nn dot func. So I'm gonna using that nn dot sorry. So this nn dot functional library over here that we use over here. So f dot normalize. Come up. F dot normalize x, right? And return x. I'm gonna do that. All right. Now let's see if it still works. Yep, still works well. All right, so now you see like why exactly I put in those small helper functions wherever I can is to bring in as much flexibility as I want. And now imagine like what the only thing that I need to do now is whenever I need to change any sort of function, all I need to do is I need to copy paste this def mnest preprocess, paste it wherever and do whatever changes I want. And the model now is going to always have that modified functionality. So I'm bringing all of the pre-processing steps into one small function. It basically takes care of the batch size issue. It takes care of the normalization issue. If you want to do something else, like add in an extra channel that corresponds to something else, you can do that over there. That's that. And I'm also going to be copy pasting my learner class, that big class that we used before. All right. Let me, or let's actually build it from scratch. I think it will be quite, it will be a good learning experience for us. So because I want to reiterate like because I think the learner class, I mean, may have flown over your heads. I mean, what exactly was doing. And also it's very important to see everything in a very step-by-step manner, in the sense that what exactly is happening with the data at each step. So the class, there's an init, there's self, there's trainDL, there's validDL, all right. Model is equal to get CNN model now, okay, which is by default, and optimizer equals none by default. Is there an indentation error? Okay. So first of all, for self trainDL is equal to trainDL, self dot valid DL. You guys can copy paste it from last time, but I'm writing this from scratch because I want to show you important things over here. Self dot model is equal to model, self dot opt is equal to optimizer, self dot model dot parameters. Oh, so, and then dot sequential also takes care of this, dot parameters, dot modules, everything. So nn dot module, nn dot sequential is basically your easy way out of creating a PyTorch model. And we actually constructed each of that from scratch last time. So now that we've understood how models are built, we don't actually have to use them again and again. So we're going to be using functions that are already predefined. Even these functions, like over here, you see over here, next lab onwards, we're going to be using predefined functions as such, like whatever PyTorch uses, because we've understood them. Okay, so this is also part of your homework. Please understand them. Homework, understand the working of this loss function below. We did discuss this last time, so if you guys want to understand it again, probably go back to that lecture, search on the internet, do whatever you want. If not optimizer, otherwise if optimizer is mentioned, just simply use that optimizer. Now, why do I exactly use this is because I have the ability to use any optimizer. Let's say, for example, there's an optimizer known as the Adam optimizer. Sorry. Yep. And I can simply put in this optimizer instead of the generic optimizer that I've defined. All right. And it's going to still work well. All right. Anyways, we'll take a look at that as well. So I'm putting a comment over here, show working with another optimizer. And so now you have another layer of flexibility that you can do whatever you want. All right. Def fit, which we used before. Self, number of epochs by default it's going to be 1. Batch size is going to be, okay, I don't need batch size actually. Layer, so LR is equal to none by default. Okay. And loss func is equal to NNL. All right. Now, in this optimizer, I've actually defined a very generic loss function. So first, I'm going to be saying that self dot opt dot lr equal to lr if not lr, which means that if lr is not none, or if lr is not none, okay, else lr itself. Okay. Now I'm going to say for epoch in range epochs, right? What's your very first step? You first do for x comma y in trainDL. So you're iterating through all of those. Now, let me do one thing. Let me redefine if mnist preprocess. Now I'm going to be including the GPU functionality as well. Okay, why over here? I mean, I'll just probably do it over there only. But it's a good exercise to probably do it over here. I'm going to pick this. I'm going to say, well, not over here, actually. I'm not going to put it over here. I'm going to define another okay. So I need to do actually put them into GPU, and so the way to do that into GPU is to, so the GPU in Linux-based system is actually known as CUDA. And so CUDA is actually a very NVIDIA GPU specific thing. So which is why, like, you can actually run it on your own system if you want, all these GPU things, but only if you have an NVIDIA GPU. Because CUDA, which is actually the driver that supports all of these CUDA operations, is only supported by NVIDIA. So in order to put them into into CUDA, so what you do is basically x comma y. So if okay, the way to actually check for if GPUs are available is torch.CUDA dot is available. Now it's returning a false because we have not activated a GPU. All right, but I'll show you what happens when you actually do that. So if torch.CUDA dot is available, so if this is true, x comma y is equal to x dot CUDA. All you need to do is that, okay, in order to run anything on GPU, so I'm just going to be putting this as an extra note. To put the model, to run the model on GPU, one, put x comma y on GPU. Number two, put model on GPU. That's it. All right. And the way to put anything on GPU would be x is equal to x dot CUDA. Right? Y is equal to y dot CUDA. And model is equal to model dot CUDA. That's it. All right. So now learner function here. X dot CUDA, y dot CUDA. All right. And model dot CUDA as well, right? So self dot model is equal to self dot model dot CUDA. That's it. Right? Else, just keep it as is. All right. All right, that works. And I'm going to be passing everything. So now all I need to do is loss.
Bhaiya, why are we doing this inside the for loop? Why can't we just do it once outside?
Oh, yeah, you're right. Good point. Good point. I mean, anyways, see, x's and y's have to be done inside the for loop because they're extracted only within the for loop. Now, this I can probably optimize this. I can take this out and put it over here. All right. So if torch dot CUDA dot is available, yeah, I mean,
Can't we do something like a train DL ko entirely put it on GPU and then I don't know if
yeah,
it'll be
yeah,
that.
sure.
I mean, it's fine if this also this is on this.
No. Good point, Nick. Very good point. Let's actually take a look at how to actually put things on a data loader. And let me see if there is a functionality that now essentially what you would have to do is that the problem with why I can't actually directly do is that, I mean, are you saying that at the very beginning I would run a for loop over here and extract each x and then put it into the PyTorch data loader, right?
Yeah, like the whole thing together.
The whole
Whatever
thing
we
together.
just.
But the problem is when you're extracting X and Y, it's out of the data loader. Data loader is not affected at all. So you've essentially taken a copy of that
Oh,
X and Y,
yeah, yeah. Hmm.
but there might be a way to actually put it on the uh, on the GPU through the helper function itself. Like PyTorch may have some sort of internal function to do that. Let me actually see if I've seen anything.
Hmm.
Let's Google it. Put data loader on GPU. Okay, it's the very first search. PyTorch. How to load all data into GPU. Okay, let's see. Okay, so this would probably push an error, but let's say you all you need to do is traindl dot two and then the device which you're using. So over here, the CUDA device is usually CUDA 0, which means that I mean the GPUs are actually numbered. So people a lot of computers have multiple GPUs, so they're named as CUDA 0, CUDA 1, and so on and so forth. You would do something like this, but it would throw an error because it does not have an error. So you push. Okay. The data set has to be converted into that. So okay. So data loader itself cannot push it into the GPU. Or probably have to do something like mnist in images dot two. Let's see if that exists. Attribute errors. It's not an error. CUDA 0. Attribute error. Okay. All right, we'll take a look at this. Actually, it's not really. It's actually quite hassle-some.
Yes, okay.
We will take a look at it. I've personally never used like in order to preload everything on the GPU in the beginning. The reason being, the purpose of the GPU is to accelerate your training, but your data itself is so large, the GPU cannot handle all of that data at once. Like it's essentially the same as the data currently over here is on your disk, all right? Is in your RAM. Now you have a lot of RAM, but you don't have a lot of GPU RAM.
Yes, yes, understood.
Yeah.
Hmm.
So which is why I never recommend doing that. But since over here we just have 60,000 images and each of these images are very small, it's a few kbs. It's not really a bad idea to do so, but it's not efficient. I
Okay.
would never recommend anyone do that.
Hmm.
But having said that, there are ways to do that. So, and you can search them on the internet. But not recommended because you don't have enough GPU memory. So essentially what you do is whenever you get the data, you simply put it on the GPU and then later on we remove it. Okay. All right. So next step would be loss is equal to nnl self dot model x comma y. All right. Then loss dot backward. All right. Self dot opt dot step and self dot opt dot zero grad. Right. Simple functions. We've always used them. We also did an accuracy function, which basically meant that accuracy is equal to 0 dot, and then we did I is equal to 0. So now this is validation accuracy measurement. We don't usually care about the training accuracy because I mean you do, but like if you had to choose between one, it would always be validation accuracy because that actually tells you like how good your model is performing. So for x comma y in valid DL, now I don't need to probably put it into your model as such. I mean, your GPU memory as such, but still I would probably do that. So I'm copy pasting these two lines. All right. Right. What else next? And X. Accuracy plus is equal to accuracy self dot model x comma y. I plus is equal to 1, and basically print epoch plus 1, because epochs go from 0 to n minus 1, so plus 1. Validation accuracy by I, which is basically averaging across all of them. Now, there are actually ways to do that. You could have simply created a list of accuracies and done a mean across them, but this is sort of more memory efficient, I guess. And we don't guess you should always try to save some memory. And we also defined this function previously, which was def predict, which was self comma x, which is simply return torch dot argmax. So it, instead of giving us a tensor of 16 comma 10, it's going to give us 16 comma 1. Basically, for each of the 16 tensors or any image, it's going to return us with that particular whatever whatever is the prediction of the model. Model x, time is equal to 1. All right, that's done. Invalid syntax. Oh. Yep, works. Right, so model is equal to get CNN model. Now we are running a model, right? Opt is equal to optimizer model dot parameters, right? Learn is equal to learner NDL valid DL. Model is equal to model. Optimizer is equal to opt. Right, and basically I'm going to do learn dot fit 10. Hopefully it works. There will be some error. Oops. Classes equals 10. No CUDA GPU available. So I think where is it? 5 frames. So now you see, because if torch.CUDA is available, okay, yeah. Okay. I forgot to put my brackets over here, and so because of that, it returned some string, and because of that, strings are like by default considered true in Python, so it went through that. Unsupported types of operands for star, none type, and tensor. Self.lr. There's some mistake with LR learning rate. If LR is not none else. Oh, I don't need an else. Why don't I simply remove this? LR. Wait. If LR. Yeah, it's working. All right. Wait, why is it printing so much? Did I ask it to print anything? Yeah, okay. So from my previous lecture, I think I must have left something over here. Now you're going to see that it's going to be running. It's going to be very slow because, mind you, we're running all of these operations on a GPU, which is what sorry, on CPUs, which is what GPUs existed. Because these operations are basically a lot of multiplications and additions. CPUs are very versatile, but they don't have a lot of multiplication and addition operations, which is why GPUs came into the picture. Now, you guys might know GPUs are, oh, by the way, we are at 95% accuracy in the very first epoch, and we are running for 10 epochs. And by the way, we reached some 90% accuracy with a linear layer, with a standard multi-layer perceptron layer in like 10 epochs. So you guys see that this model is now working well. All right, so you guys have built your computer vision model. I'll take, yeah, sorry, please, sir. Someone was saying something.
Why don't we run switch on the GPU runtime?
I'll do that. Give me a
Oh.
minute. Give me a minute.
Hmm.
I want to show that how model development is done. I want to see if everything is working, and once we're done with that, we'll turn on the GPU. While I'll do this, let me actually give you a story about what GPUs essentially are. So, if any of you are into video gaming and such things like that, you might know that um, uh, GPUs are actually used within video games. And the reason why video games actually use GPUs and not CPUs is because GPUs are basically like dumb creatures. Okay, they don't have a lot of flexibility, but they're very, very good at doing what they're meant to do, which is a lot of multiplications and additions. Which is essentially, if you look at it like video game graphics are nothing but matrix multiplications. All right, that's all that they are. Which is why CPUs are actually very versatile, but they don't have a lot of memory or like resources allocated towards multiplication and additions, because CPUs have to do a lot of things. GPUs are specifically meant to do these multiplications and additions, and they do them very fast, which is why they were used in video game graphics and so on and so forth. And if you guys think about it, what exactly is deep learning? Deep learning also is a lot of multiplications and additions, a lot of W times X plus B's. All right, which is why GPUs are so fit for deep learning and so on. And now you actually have things like TPUs. TPUs are nothing but GPUs with lower precisions, because people realize that GPUs, I mean, video games nowadays are so high quality, they require 64 bits. Like, if you guys have read about computer architectures, you know that like the way computers actually reads those bits is they have a floating integer point, and then they have a mantissa point, which is like there's a sort of a decimal point system that goes on. Something after the decimal point, something before the decimal point. And now systems are like 64 digits after the decimal point. So like that's the amount of precision that computers can work with. And that might be actually useful for video games, because you're actually talking about like very fine coloring. Like you're actually talking about like a lot of shades of colors, and video games actually want to show that. But people actually realize that you actually don't need that for deep learning, so then they made TPUs, which is basically GPUs with lower precision. All right, it's running. And you're seeing that it's taking more and more time now, right? Like our training of the logistic regression model was quite easy, but now this is very, very slow, because now it's running on a CPU. We need to run it on a GPU, and so we'll take a look at how that is done.
Sir, here we can see like from epoch 7 to epoch 8, the validation accuracy actually dropped.
It did not drop as much. I mean,
It did not drop much, but like,
hmm,
can we say that that is an indication of overfitting?
no, not necessarily.
Then why did the
Uh,
drop? Like ideally it should keep on increasing, right?
no. Did you guys remember that very first graph that I showed you, that parabola in which that it sort of goes down and then it keeps on sort of
Mm-hmm.
oscillating? Now,
Acha,
because
so it passed the point and
it
then
passed
it's
the
going
point
back.
now,
Okay.
because the learning, because we've not changed the learning rate at all. Like, because the learning rate is constant throughout. Now there are actually ways to do that. Now people, what they do is that they actually change the curve of the learning rate, so the learning rate sort of decreases towards the end, and it sort of becomes more optimized.
Okay.
Now let me remind you that validation accuracy reducing is not the is is not the indicator of overfitting. So overfitting and underfitting will never be determined by accuracy itself. As a rule of thumb, always determine the accuracy through loss functions. Okay. And also the difference between underfitting and overfitting is not a drop or sort of like a single change within the values of the loss function, because there are always a lot of random things that goes on. The way to actually determine underfitting and overfitting is to find trends within training dataset as well as validation dataset. The way to look at overfitting is if your loss of training loss is reducing and validation loss is increasing. That's the sign of overfitting. And you need to look at trends. Like that is the proper way to analyze.
So could you repeat what is increasing, what is decreasing?
If the training loss is decreasing and the validation loss is increasing,
okay,
that is overfitting.
Mhm.
Underfitting is the opposite of this. Is basically when training loss is increasing and validation loss is decreasing.
Mhm. Yes, so I
And
guess
when they're
when
both
you're
decreasing,
training,
that's just right. Like that's the proper fitting curve.
Mhm.
When they're both decreasing. So you need to look at trends and not the absolute values or absolute changes.
Okay, yes, sir.
Let me actually put this into a GPU now. So what you need to do is that go to your runtime option over there at the very beginning. All right. Go to change run type and do and select the GPU over here. All right. Save it. And now you need to actually run everything again because now your GPU doesn't know what's going on. So you need to run all. All right. So I'm going to run everything from top to bottom. Now look at this. It's still taking time. So there is some error, which means that we have not properly fed this into the CUDA machine. Take a look at what exactly is happening. Wait. Torch.CUDA is available. It's true. Right. So X and Y have been put on the CUDA. Model will be put into the CUDA. It should ideally work. I have no idea why it's not working. There is some issue. So we'll take a look at this. What exactly is the error next time or so? But let's move on for now. But anyways, it's not really that big of a deal to put it on the GPU. It's very easy. We'll look at it. I'm probably missing just like one line of code somewhere, and it's creating the error. Anyways, let's actually build more complex networks now. So let's actually move on from this very simple generic network that we see. And so now what I'm going to do is more complex networks. I'm going to take in a more complex data set. All right. And I'm also going to be creating sort of complex neural networks as well. For this, what I'm going to do is that I'm going to actually show you a very important skill. Because how do you actually build your own data sets as well, like from the net? And so we're actually going to be scraping the web to actually build our own data set. So right now I'm going to be picking the cat versus dog problem again. All right. So cat versus dog images. And I'm actually going to be taking images directly from the internet to do that. And so I'm actually going to be showing you how this works. I'm going to be installing a library which will help me like do this web scraping. Right? And it's called JMD_image scraper. What it essentially does is it uses this browser known as DuckDuckGo, to sort of scrape images from the web. Let me install this. And you can go over here and check, look what exactly it does. GMD image scraper. Yep. Libraries for creating deep learning dataset. It uses DuckDuckGo for image scraping as a return nice big images and have some rather nice parameters to make your life easier. That's how you work with this. This was made by this guy known as Joe Dockrell. Wonderful. He actually contributes a lot to the community. So I'm just following the tutorial over there, like how to import stuff. So GMD image scraper. By the way, you're going to use this. It's going to come in very handy for you guys when you're actually building your data sets as part of this assignments in this over here. I'm bringing imports. I'm going to do import star from pathlib, import path, root is equal to path.cwd slash image. So I'm going to be creating a folder, right? And I'm going to be doing DuckDuckGo search root, which is where images were going to be passed. I'm going to name that root folder cat. On the internet, I'm going to be searching for the word cat. So look at this, how this works. There's the documentation for that. And so look at this. What's going to happen is you're gonna name a folder name as cats. On DuckDuckGo, you're going to be passing this keyword. So whatever images are going to pop up on DuckDuckGo because of this keywords, it's going to download those images. And you can also choose how many images you want to download, right? So I'd say 200 images right now would be good. So I'd say max result. So I'm going to be creating a data set of 200 plus 200, which will be 400, right? Why is this capital? Let me just name this small only. All right. Similarly, I would do DuckDuckGo search root dog on the web, also search for a dog. Max results equals 200. All right. Let's see. Now I'm downloading the images. Look at this. So in about 18 seconds, I downloaded 200 images. We'll take a look at what exactly it looks like. But let me just continue writing. And I'm going to say from GMD image scraper dot image cleaner import star. All right. And I'm going to do display image cleaner root. What essentially it's going to do is going to display all the images and give you a chance to sort of delete any sort of mismatches, or let's say, sometimes you're going to be passing a dog and it's going to give you a woman, like 3 women and a dog in between. So that's going to confuse a model, and you don't want to pass those images in because they're noise to the model. And so this is going to give you an opportunity to sort of clean the images, sort of delete whatever is not required. So let's go over here. Let's take a look. Those are cats. All right, look fine. Let's go to the next page.
So how does the image cleaner work? For that, wouldn't it itself have to be a neural network to recognize what is a cat and what it?
No. This is the data set. These are labeled as such. Like, see, we downloaded images of cats into the folder name as cat. So look at this. If I do an ls over here, look. There is a folder name as images. So I do cd images and then ls. Okay, maybe cd images / cat. Okay, so these are images of cats that have been downloaded from DuckDuckGo because we entered the keyword cat over there. So they are labeled as cats. So now if I go over here, this is sort of you see that this will be a cat. I don't know why it's not displaying. the label itself. But anyways, you have a chance to sort of delete what you think was going to confuse the model. So for example, I'd say this is going to confuse my model, even though this is a cat, but I'll probably delete this.
So let me. Acha, the user, we manually have to select what we want to do. Oh, that was my question. I thought the function did that automatically, and I was like,
no. You have the chance to sort of take a look at the data and sort of
yes, I got it.
yeah. All right, so these all seem fine to me. Yeah, these are all cats. Yeah. Yeah, so these all fine seem fine to me. I mean, you can keep on going searching for whatever you want. All right. I'm gonna actually have to change a few things. I'm gonna actually create. I'm gonna have to create a data set because these are images. Now, previously we had data sets, and data sets have certain properties. So we're gonna look at like how data sets. Have we talked about how data sets are created in PyTorch, like the class for a data set?
No, I guess you just used MNIST, which is already available.
All right, so we'll take a look at what how data sets are actually created, like the class data set, the dataset class, what is actually the meaning of the dataset class. All right, so simple as that. I'm going to first have to import from torch.utils.data. I already imported my data loader, right? Now I'm going to have to import sort of a class for the dataset itself, because it has some, it's actually very similar to nn.module. Like it's going to give us certain features, properties which you don't want to worry about. I'm going to also import random split because I'm going to have to split it into training and testing manually now, right? I'm going to have to like go iterate through my disk, and in order to do that, I need to import this library which is known as OS, operating system, and PIL because I now have images, so I need a way to handle images into tensors, right? PIL import image, all right? Right. I'm gonna create my class which is known as cats versus dogs. Cat versus dog dataset. Okay. Cat versus dog dataset is going to be a child of the dataset class. All right. That's and so there will be a def init, right? Self, comma something something. Okay, we'll take a look at this. Now, what essentially is a dataset class? Dataset class is nothing but a PyTorch class which has three properties apart from the initialization, of course, which is def len. Very important concept, by the way. Def len, def get item. Why do I have a hunch that we have actually looked at something similar to this? Maybe we haven't. Never mind. Def, yeah. So these three things. Sorry. So sorry. Init, len, and get item. So these three properties are there in any data set. And so what is the purpose of all of these? Here is the purpose. Any date. So let me look at this data set over here. Over here. So I had MNIST train images, right? So this is a data set. MNIST train images. Now I have two things that I can do. I can actually iterate through the data set like using indexes. So if I want the very first data point, I can just simply do a 0 over here. It's going to return me a tuple, which is going to be X and Y. I can do 100 over here. It's going to return me the 100th element, and so on and so forth. So this is actually possible, like indexing is possible because of dunder get item. Okay. And you can also do dunder len. Yeah. And so that is possible because of dunder len. So when you're actually doing len of something, len is a function of Python, which always goes to a class's dunder len. Yeah. So if you have not defined it, it's going to give an error. So for example, if I were to simply remove, let me actually show you something cool. Like, so to actually just show you like what exactly I mean by that. MNIST train images dot underscore len equal to lambda. Take nothing as input, but maybe self. Okay, and return hello. I don't know if this works or not, but let's see.
Are you like trying to redefine the underscore len function
Yeah,
for
yeah,
the
to show you like what exactly is going on. Okay, but this is actually quite complex.
I think there's a B in lambda.
So, yeah, it should be, and it
So,
should be
yeah.
a function, right?
No. So lambda functions are actually a thing. Oh, sorry. I'm just train images.
No, sir, as in the underscore len underscore, it should be a function, right? After that, or no?
No. It should not. We actually covered lambda functions in the 0th lab section. If you want to take a look at it, take a look at it. Okay, anyways, does not matter. My point is that whenever you do a len, it actually like sort of accesses the dunder len. Can you guys give me a second? Sorry, guys. So so our initialization function. I'm going to take this lab for 10 more minutes maybe, and then we'll continue next time. All right. But it's not actually very difficult. So what I'm going to do over here is that I'm going to be sort of and what I'm going to do is I'm going to be copy pasting a lot of code, and you guys, I'm not going to actually covering this section because it's sort of optional as such. It's not optional. I mean, it contains a lot of important things, but I'll expect you guys to actually sort of go through this this pieces of code, which would be extensions of whatever code that we've written till now. All right, and it's going to be basically a sort of more advanced version of whatever we've done over there. But take a look at this. But for now, I think data set is an important concept. I'll teach you guys what exactly is happening over here. Root is basically going to be images, like, because I've by default like put everything over there, and transforms, right? Because I want to have the ability to do something to that. All right. So self.classes is equal to this is a dictionary, by the way, for I comma v. Enumerate os.listdir. So listdir is basically going through that root or that directory and actually listing down all of the files that exist over there. So cats and dogs. So that will be my classes names, and I'm going to be passing them into self.classes. Self.transforms equal to lambda x. If not transforms, so basically do nothing, else transforms. Take a look at this lambda functions if you guys are not clear with what they are. We've already covered them in the lab 0 section, but quite interesting. They're basically one-liner functions. So this is actually a function in itself. self.x is equal to, initially I'm going to be, since, I mean, ideally I want to be passing my x's and y's separately, and x is going to be tensor, y is going to be the category, so on and so forth. Okay. I'm going to be iterating through each of the image in the root directory. So for that, it's a very standard function for PDF in os.walk. Take a look at os.walk's sort of what do you call documentation. F is basically going to be a list of all the files that exist in any directory. D is going to be the name of the directory, and P is going to be the name of the parent directory. So for file in, because F is going to be a list, so file in F, if file dot ends with .jpg, which means because there are actually going to be other functions, other files that exist over there. Some like there may exist some other file, but we are only concerned with JPG files. .jpg. So I'm going to need to open this. So self.x.append image.open path p / file. So I'm passing in the sort of the name of the sort of I'm going to have to name pass in the location of the directory of the file. I'm going to pass it through this image library. So I'm going to basically get objects of the images themselves. So by default, even MNIST dataset by default returned as images. And I want to give users the ability to do that. I don't want to directly convert it into tensors. I only want them to convert it into transforms when the user specifies that through the self.transforms argument. So by default, I'm just simply going to go self.classes path p dot stem. Now, why I'm doing dot stem is because if you look at this, one of these, this is going to be the parent directory, and this dog is going to be the stem. So I only want that. But computers don't understand strings, so which is why I actually converted them into indices over here. And so I'm basically going to be passing the indices corresponding to them. Take a look at this later on. So that's my cat versus dogs. And optionally, I want to apply transforms onto them, right? So I'm not going to be doing that in the this itself, but I'm going to be doing this in dunder get item. All right. This is going to be simply return len self.x or self.y, doesn't matter, but one of them. And that a get item will be returned. Now I need to actually apply the transform onto that. So self.apply tfms, and I'm going to be defining a function corresponding to that. Maybe
Yeah, isn't len Python defined function?
len is a Python defined function, but again, as I said, len only applies to classes. So for example, when you do len of a list is also a class. And what len does is, if you go to the definition of len, len basically, so the definition of len is basically return dunder len of whatever class you're passing in. So you need to define dunder len in order for len to work. Like how does len function know what is the length of the data set? Data set is a class which contains x and y and something else and self.transforms. And how does len function know what to return? Do you get my point?
But you're essentially using len only inside the...
Because x is a list, and lists already have a dunder len defined in them separately.
Okay.
So it's going to return a value to me. See, I'm using another data structure over here, which is predefined. List is not a class defined by me, but if it was, I would have probably had to, take care of the dunder len over there as well.
Okay.
I'm going to be defining a function over here which takes in self as well, self x and.
Are there underscores missing after init?
Oh, sorry. Point. So self.tfms self.x I and I'm going to also have to pass in the list of the transform. So it's going to be self dot transforms, and I'm going to have to return self dot y I. All right. Self dot tfmls is basically for tfm in tfm list, which is transform list. X is equal to tfm x. All right. Return x. And that basically is your data set. All right. So now let me actually show you data is equal to cat versus dog data set. Transforms is equal to, now I want to convert it into a tensor. All right. So torch vision dot transforms dot to tensor, right? But transforms, yeah. And also now, okay, now here's the problem. Now, if you guys remember that our batches were 16 times 1 times 28 times 28 in MNIST, that was only because like all the images were of the same type. So one type 28 by 28, which is why they could be converted into one big, they could be concatenated together, right? But over here, we have downloaded from the internet and they're not going to be of the same size. So we're going to have to manually crop a size which is consistent with everything. So I'm going to be using a center crop, which basically means that take out a certain part of the image, like a square image from the middle of the image, called center crop. Size is equal to 300. All right, let's take a look. Those transforms, not transform. Yep. So now I'm going to do len data. Len data works. So they must have been. So why are they not? Why? So why are there 400 images? Because if you remember, we deleted one image, right? So there are 399 images, and now if I do data 0, I can now index it. It's gonna give me this. So now you see why I mean, like, this was a class which you defined from scratch, but now you can use len on this data set because we defined dunderlen, and we can index it because we defined dunderget, right? So this is what essentially a data set is. All right. So now you know about that as well. I'm gonna have to do a train test split. So all right, I'm gonna stop this lab session over here. But please take a look at this lab notebook by evening today, because it's gonna have a lot of interesting stuff. All right. And I expect you guys to go through that, understand it. Mail me if you don't understand anything. All right. And so we're essentially done with the basic fundamentals of computer vision. All right. And next time we're actually going to be looking at more advanced applications of computer vision, like image segmentation and stuff like that. So see you guys next week, and I'll stay over here if you guys have any doubt.
Just one question I had from last week's class.
Sure.
Was in the MLP class, you wrote a function, a forward, to do the forward pass.
Right.
But when you were writing the learner class, usme in fit, you just did a model of x instead of model dot forward of x.
Even last time we never did model.forward x. We just did
In
model
this,
x.
yeah,
No,
I'm talking
even,
about last time only.
sorry.
In last class only, I was asking.
Okay. Take care. Good question. We've actually talked about this, but let's go to nn dot module definition. Okay, what exactly is? Okay, so whenever okay, let me define a dummy class for you. All right. So class. Okay, it's not going to inherit from anything. If init self and name. Okay, so I'm gonna have to put in a name over there, right? And so I'm gonna say self dot name is equal to name, right? And I'm gonna write. Okay, let me pass it through nn dot module for once. Okay, and now let me pass it through. Let me write a def forward, and the purpose of def forward is it takes in a number and it sort of returns the twice of that number return. All right. right? This is a class. So let me say person is equal to Palash. Name is going to be Palash. Okay, let me actually rename this into something, but okay, this doesn't matter for now. So this works. In order to execute person, I simply just need to do %2. Oh, self-attribute name value none. Oh, I forgot. Okay, whenever you're using nn.module, always super.init, always necessary to initialize the upper module, because otherwise it won't work. Yep, it works this way. Now, the reason this works is because there is actually, let me actually comment this out, and let me write this another dunder function which is known as dunder call x. All right, self comma whatever argument you give to us. Right. Now let me say return 2 times x.
Is it like function overloading or something?
Not overloading. I actually don't know the exact name for this, but so calling of a function is actually in deep learning a lot of, so one of the very basic like components of object oriented programming is to actually use objects in terms of functions. Like everything should be an object in object oriented programming. Even if you want to execute something, it should be an object, right? So you need a way to execute that function within that object, and that is actually done using this dunder call. Okay, giving you a new concept right now. Okay, so now you can actually use this class as a function by simply using it as a function, and whenever you do that, Python internally calls dunder call. Okay. Now, what nn.module does is that it actually gives this dunder call another name, which is forward, because it makes sense. Because when you're passing it through a neural network, it's called a forward pass. So it's essentially a function. So Python has essentially done nothing but renamed this as forward. So how nn.module is defined is basically return forward of x. Basically, this is the internal definition of nn.module.
So the name can only be forward, that means. Or if I change the name from forward.
Because it's convention, otherwise you'll have to change the dunder call as well.
Oh, okay. So okay.
But it makes sense, no? Because it's a forward pass. Similarly, when you calculate a gradient, it's called dot backward. It's called dot backward for a reason. Now you can name it anything, but you'll have to change the source code.
Yeah. Okay.
Yeah. So that's the concept.
Thank you.